Welcome, everybody.
Yeah.
Welcome to the Cyclone DDS and ROS presentation. My name is Philip Oetinger, and this is
Troy Harrison, and we're software engineers working on Cyclone DDS at ZettaScale.
This is the fourth webinar of the Cyclone DDS Unleashed series. The series began with the conception of DDS as a technology and has touched upon the issues and solutions for using DDS within complex topologies and how to improve internode performance using shared memory. In this webinar, though, we want to explore DDS and its place within the ROS community.
Yeah, and so, the point is that Phil and I here, we're coming to this as DDS developers, like interacting with ROS, and we're sure that many of you are ROS developers or ROS users coming here to learn more about DDS. So it's important for us to first put ROS in context. What is ROS? So it's a consolidated platform, right, that unifies all the intricacies of building robotics applications. And so, there's a whole load of moving parts when you're constructing robots. And so, for example, as part of the parts, hardware. So you have sensors and you have actuators, right? And you have the device drivers for getting information from those things and communicating with them and controlling them. And so when you have, your sensors or your LiDAR or whatever, you want to take that information, you might want to view it in something. So you might want to put it in a simulation because you don't want to actually run your test bed and your developments on, live on your actual hardware.
Let's turn on this $1 million arm and see if it works. Let's simulate that first.
Yeah, let's simulate it first. And so then on top of that, right, once you have your simulation state and your real world state, you might want to do digital twinning. So then have those states be synchronized. And, that opens up teleoperation and a whole bunch of other interesting things there. And then you have kinematics planning with Move It and et cetera, et cetera, et cetera. So ROS unifies all of those different moving parts and makes it easy for you to start constructing your robotics applications. ROS used by millions of developers and users, and it's across a huge, a very wide range of robotics applications. So for example, you have the Indy Autonomous Challenge where you have cars racing autonomously. And they're going, hundreds of kilometers per hour, or you have robotic farming equipment, right, in fleets, where it's all these automated fleets, and those cost millions to develop, thousands, tens of thousands to deploy. But also you have ROS being used for small toy robots, basically.
Yeah, hobbyist robots.
Yeah, or the turtle bots, right, where they're used as learning aids or as demo platforms and stuff like that. But it's basically incredibly hard to overstate the impact that ROS has had on robotics. And the trickle effect it's had on everyday life. And, you have those robot vacuums and these things, they're all present in many people's homes nowadays.
Yeah, I have one. So yeah, both internal and external communication is kind of critical to the functioning of 100%. These robots. So internally, you have the sensors, actuators, the processors, they all have to communicate, but also externally. Yeah. So maybe you have robots talking to robots in a fleet, or you have maybe a spacecraft orbiting Jupiter and you're talking back to the base station, without access to this, to the information in a timely manner, well, nothing's going to function.
Yeah, how can it work?
Yeah.
And so, with that said, networking is obviously critical. Right? Your network communication is critical to your robotics applications. And so, DDS, we want to talk about the networking side of things. Yeah. And so with that in mind, it's important to talk about the constraints.
Yes.
So we came up with a set of constraints for, what we thought were very prevalent and important for any networking solution operating in the robotics space. And so, for example, bandwidth, you take those sensors and you might have LiDAR, point clouds, image streams, or other telemetry, and all of this is being at a very high frequency. And so that's megabytes, gigabytes worth of data, right? And all that data has to show up on time. So you have a latency budget. If that information isn't there on time, then what are you going to do?
Mm-hmm. Exactly. For example, I've seen videos of those robots playing ping pong. And catching a ball in real time, or drones flying in fleet formations. All that, it looks like it has to see, react, and do instantly.
Yeah, very, very. Yeah, the latency it has to be high. It has to be. And so then on top of that, right, reliability, that's sort of an obvious one because, well, when you need the data should be there. Yeah. And also when you need the data should be there and the data should be correct. Yeah. Because if you don't have the correct data coming in, then things can go very wrong very quickly.
When you send the kill signal, say something's malfunctioning,
yeah,
it better get better.
It better stop. Yeah. And so sort of in the space of like, like safety critical and security and this kind of stuff, in that vein, you also have security. And so, like conventionally, you're talking about cyber security, right? So you want to prevent bad actors from accessing sensitive components or information. And this is, you could argue here, this is sort of dependent on your threat model, right? Like my LAN is secure. That's fine. That's okay. I don't mind if just make that secure. But the point is that nowadays, as things are developing further, more and more like you want teleoperation, right? You want your data to be distributed out of your network, like exfiltrated, so that you have like a dashboard or something for other people to like react to. So more and more you'll have in these systems some form of wireless uplink present in the network. So from a cyber security perspective, it's like important to also consider security.
Yeah, definitely.
But also like we have some customers, right, who make use of like the DDS security spec, so the stuff coming out of the DDS security spec, to ensure like the confidentiality of their like proprietary systems. So they'll encrypt their communication on their deployed systems, so that people can't just eavesdrop and like reverse engineer the protocols and stuff like that. So both from a cybersecurity perspective, but also from a confidentiality perspective, security is important to consider.
Another important constraint would be the footprint.
Yeah, and that's also
exactly. So some robots might have as much resources as they want.
Yeah.
You have an infinite budget, great, But other ones, they might be small. They might have small boards, limited in their RAM, their CPU cycles. Yeah. Maybe they're battery powered, so they have a finite lifespan. And it's important here at ZettaScale, not only to provide quality
and like from an efficiency perspective, not just from an efficiency perspective,
but it would be good to make sure that we help the planet, and we want to be ruthlessly efficient to make sure we're not wasting.
You shouldn't be wasting resources. Exactly. And sort of like in lieu of this, or following from that, like feedback from your networking, because, for example, if you have deadlines, right, for messages to come in, and those deadlines aren't being met, it's important that you receive feedback because something's going wrong potentially. And the way that feedback should be provided to you, it shouldn't be like poll based. You shouldn't be like while true, are things okay? Right. So it's important that it's provided to you sort of a signal, push based mechanism. And so these are the things that we thought were important for like the constraints in robotics in networking for robotics applications. And so with that said, right, we can talk about the actual like current backbone of communication in ROS2, which is DDS. And so here we have like the architecture that's present for like when you're using ROS2, you'd have your user application that's using the ROS APIs. Those APIs might be present across like the language bindings that ROS provides, so like C++ or Python or Java or whatever. And then you have this underlying layer that lives underneath those language bindings, which is sort of the ROS framework. And there you have like scheduling and actions executing and like logging, and node lifecycle stuff, all that kind of stuff. But underneath that, you have this RMW layer. So that RMW layer is the ROS middleware, and that represents the communications backbone of ROS. And for ROS2, that communications backbone is based primarily on DDS. And so, DDS, it's like a well-defined specification that's matured over like decades. And so because it's open and interoperable, you have these different vendors that you can plug at the bottom, so it prevents vendor lock-in, the choice of using DDS here. And like when you look at ROS2, like let's say topics, services, and actions, you'll see that they map basically very thinly as just convention on top of DDS. Yeah. So you have like the ROS2 topic here, ABC, and then it's prefixed, it's just the DDS topic is the prefixed form of the ROS topic. And then services and actions, you have some more topics that are used there, like for example, for actions, when you have a robot being asked, please rotate, then it has to have a channel to be able to provide feedback on like, I have this much left to go, I have this much left to go. Yeah.
The world isn't perfect, so you have to have that.
Potentially also, you want to react to things, and if you want to cancel early, So those actions have a whole bunch of additional topics that are made, but they're still just DDS topics. Yeah. And so, we're dealing, we develop Cyclone DDS, and so we want to now provide more detail on DDS, like in ROS, keeping in mind those constraints, and we'll be doing it focusing, in the context of Eclipse Cyclone DDS, because that's what we work on.
Of our implementation.
So yeah, what are the benefits of like DDS in ROS? And so again, keep in mind those constraints that we had mentioned previously, right? So like you have reliable communication in case of drop-offs just built into DDS. So for example, you can have like sensor redundancy. You have multiple sensors, and then you can specify, okay, well, these sensors are communicating information, and sensor A, sensor B, sensor C, they have different strengths. And you can set those strengths. This has the highest strength, sensor B has the next highest strength, et cetera, et cetera. And then if sensor A like drops off the network, or if its messages aren't like coming in based on the deadlines that are set, then the next sensor with the next highest strength that fulfills like that deadline, or that's still active, will seamlessly have its messages take precedence. And when that other sensor comes back online, let's say if it dropped off, then immediately DDS will handle like handing over those messages and making sure that that sensor's messages are taking precedence over the other sensors immediately. So just seamless redundancy through failover. And harkening again to that node coming back online in DDS, like adding and removing nodes on the fly, it's very easy. It's a very dynamic process, right? As things join, they just get discovered and are able to start immediately communicating with the rest of the DDS data space that's present there. And so you can sort of create this like ad hoc network, right? Just around yourself very, very, very easily.
Yeah. And like you could maybe imagine a scenario where these nodes could be the actual sensors robot, like you said, sensors come online, offline, but it could also be entire robots entering or exiting the network. Maybe they ran a battery, or they're now entering back into the workforce. Maybe
like they were charging and then they're
exactly, like they're going back to pick some stuff in the warehouse. I don't know. But another constraint or a benefit of DDS, talking about those constraints, it's very low latency and high throughput, especially talking from our clips.
This is more of like it's not necessarily something that you like. The DDS specification was designed effectively also, but the point is this is sort of a feature of implementation. And we know at least as Cyclone developers that Cyclone is very low latency and very high throughput.
From our own experience, we can say, and also Eclipse Cyclone DDS is lightweight, so we're energy efficient. CPU cycles, we use little amounts of RAM. The install process, I think, is 20 seconds.
Oh yeah, for building, like if you're building Cyclone from scratch. It's very nice as a developer on here that it's so easy to build, because where I've worked in other places, it's like 45-minute build times.
Oh yeah.
And so this one's important, like standard. It's standards based. So the DDS specification, it's a standard. It's very mature, right? It's been developed over decades, and I think this is a very important reason why ROS had selected DDS as their like choice of it being a backbone, because since it's standard based, it ensures interoperability. There's a whole bunch of tooling around it, and it prevents vendor lock-in. And so then with this choice, ROS is not. Allows freedom for the end users, right, to select their DDS implementation of choice based on whatever their own investigations are. So now that we've discussed, the benefits of DDS and in ROS, it's I think useful for us to talk about it in a bit more detail. What is DDS? And we'll be orienting it again, from the ROS perspective. So what is DDS, right? It's the data distribution service. It comprises of this protocol, the real-time publish subscribe protocol that's defined in the specification. And it then has it has a discovery process also as part of that protocol, where when you have readers and writers and people, nodes entering the network, that they're able to broadcast their presence and immediately join in the communications process. And so if you look at the diagram here on the right, you have these these two systems, system 1 and system 2, that may be disparate systems, right? And then what they want to do is they want to synchronize some information between each other. They want to communicate with each other. So they're going to do that within the context of a domain. So that domain is just, an ID that they've chosen, domain 0, domain 1, domain, for example. And then within that domain, you have a topic. So DDS is topic oriented, right? It's this distributed push-based data space based on these topics. And if you're used to generic programming, it's just a topic T. And that T is, the data structure whose messages of that type you want to receive. So, you create your struct. It's done via there's another specification, like the IDL, the interface definition language, and you can use that to define your data types that will be communicated with via DDS. So you have that T. And then you have this writer T on one system, this reader T on another system. The writer will be writing messages of type T, the reader will be reading messages of type T, and they'll both be synchronizing each other against that topic. And DDS is the thing that's handling that synchronization.
Okay. And it's not one-to-one, right?
Yeah, no. So like in this slide, just for the sake of brevity, we just have that one reader and that one writer. But you could have many readers, many writers, you could have many systems, right? As long as they're all seeing each other, then the DDS is handling the communication and synchronization of all of that information, all those instances. And yeah, on top of this, you have this notion of quality of services, right? And these are things that you can use to specify the non-functional requirements of your system and like steer the behavior. And so, like for example, what we were talking about before with like deadlines, you can use quality services to specify your deadlines or like latency budgets. So if you have a latency budget that's 0, then messages have to go out immediately. But if you have a latency budget that's bigger than that, then you can start batching messages together. And then as long as you haven't hit your latency, like as long as you still have latency budget to spare, you can keep on batching these messages. And then when the latency budget's out, you can send everything more efficiently in batched responses.
Okay.
Yeah, and so like linking back to the description of being topic-based, and also from before where it's just a thin layer over, like ROS's API provides just this by convention abstraction over DDS. Here you have that same thing. You have that topic message there that's mapped basically one-to-one to the DDS topic of sort of the same type. And then you have like these actions and services. And, as we had seen from the table before, you have goal, feedback, and result, and those are split into multiple topics, but it's still just a very thin abstraction, very thin just convention over DDS. So, we've discussed sort of like how ROS maps to DDS.
Yeah. What DDS is.
What DDS is.
Maybe we want to explore a little bit of ROS from the DDS perspective.
Yeah.
So let's do that.
Yeah.
So here, here we have what's probably a very familiar tutorial for all of you. Turtle Sim, tried and true. So as if some of you aren't aware, I'll explain a little bit of what this is. So we have 2 applications running here right now. We have a Turtle Sim viewer on the right side. This is displaying the world. So there's a little turtle guy, he's got a jetpack. And we have the telop. So this is saying, I'm going to give it an input, and it's going to broadcast that message to the turtle, and the turtle will respond on it. Yeah. And so, as you can read in the prompt, I can control it many different ways. So I can give it relative commands by controlling it directly with my arrow keys and tell it to, hey, turn left, turn right, move forwards. I can give it absolute. So with the G, B, V, etc. keys, I can tell it to, for example, look west, so 270 degrees. There he goes. He just turned. And that was where you were saying with the feedback loop. So
exactly.
He has a goal, and he's going to try to go to that, and he'll say where he is as he's going, how long he's got left. So this is using DDS under the hood to send messages from one application to the other, and it performs based on what it's told.
Can you use the arrow keys also?
Oh, yeah. So arrow keys just to demonstrate the relatives. So I can control, drive around. Yeah. And I can go backwards. So let's take a look at what's going on kind of beneath the hood, DDS side, so the communications. ZettaScale has a tool available for Cyclone DDS.
Cyclone DDS.
And it's called
Cyclone DDS, it's just a CLI tool.
Cyclone DDS, yeah. So let's not get ahead of ourselves.
Yep.
So the Cyclone DDS tool provides a few commands, useful commands for kind of probing and
probing.
Exactly.
Yeah.
So as you can see, we can scan and display entities. We can look at applications running. We can even subscribe to arbitrary topics.
And then you can hear the messages that are.
Yeah, we can see the messages. Yeah. We can inspect types, and we can, well, that's part of Cyclone, the performance tools that we'll talk about that later. So for now, we just want to look at this turtle sim. So we're going to run the Cyclone DDS PS command.
Yep, to list processes.
Yep. And, well, we found something. Let's take a look. So we have, so we have the 2 participants. Yeah. So we know that's the telop and the display. So that's those.
And then here are those abstractions over the like
so
ROS topics and actions and stuff.
Turtle, here's rotate absolute, the status of that. So that's that loop where it's saying, oh, I'm here, I'm here, I'm here.
That's the feedback, I think, actually.
Yeah, so Where is that?
Oh yeah, down here.
There it is. Okay, yeah, you're right. As a feedback. You have other ones. So where is it? There's so many. I have one in mind that I want to look at. So let's take a look at that.
Yeah. Oh yeah,
this
here.
one. Yeah. So there's another command where you can tell the turtle, hey, I want you to teleport directly to a location, and an absolute location. Okay. So I can say go to 50-50, and it will go to that spot, and it sends the request. Yeah. Of course, as you know, there's a reply that you have to listen to as well, but we just want to look at the request. So DDS is going to inspect this. We can take a look. Cyclone DDS tool.
Here's the topic.
Yeah, so this is the topic and the DDS policies that are associated with it.
Yeah.
We can just probe or take a look at a couple of these important ones. So deadline is an important one.
Oh yeah, and this is what we were talking about before.
Yes, we were talking about, so deadline, especially in combination with reliability, reliable. So basically, with this combination of infinity, you're basically saying, I want this to get here no matter what, and take as long as you need to.
Yeah. And so this is like, if the message hasn't gone through, then you retry.
Retry forever, yeah. Some other important ones, let's take a look. So durability, so we had mentioned.
Yeah, so like durability, that's like synchronizing when you have people like joining the networks and nodes joining the network, then you might want to synchronize the histories between them, depending on that. So volatile means let's not bother synchronizing our historical data. And you can see this is sort of linked against also like history keep lost. Mm-hmm. So in this instance, you're keeping the last 10 messages, each reader, writer, and participant in the network is keeping the last 10 messages that they were interacting with. And
so if this was, for example, durability transient local, he then has 10 messages potentially.
Yeah. So then writers, if the messages that those writers have published the instances, they'll propagate to late joiners. Yeah. And so then they'll be able to populate their history just automatically.
I don't think there's any other really important ones. What else?
There's plenty that are important.
Oh, of course, but for this
latency budget.
Oh, yeah. Latency budgets.
It's right.
So right here.
So yeah, with the budget.
This is that batching thing.
Yeah. So with the budget being 0, then you send messages immediately. Yeah. But if that were non-zero, then you're able to specify, like it'll eat up that budget, and then when that hits 0 again, then it's eating up all the budget, or when it's most appropriate, right, it'll send the batch of messages.
So one thing I'm seeing, so I'm scrolling down a little bit. It does look like ROS has unset the X type ID. Yeah. So this is a problem because now we don't know what the type is.
For example. But this is like we know about this, right? Yes. So it's part and parcel actually, just because the type definitions here are like for Cyclone DDS currently there's like static, and so because of the dynamic nature of ROS, this can't be set right now.
Right.
But there's that like work's already been done on this. So there's a pull request that's merged in the like Cyclone DDS core repository, and one that's open on the RMW layer, and those implement like the dynamic types API. So then we can construct this type information just on the fly.
Then we'll be able to construct it. So right now, if I wanted to, for example, subscribe to this topic, I can't because
we don't know the type information.
I don't know what it is. Exactly. So once those pull requests are both merged, let's take a look at. Let's take a look at yours and see what it would look like once it's merged.
So over here, and I want to run like just a reader and writer common in DDS so that we can just start probing it and getting information on it. So once again, I'm going to be using the Cyclone DDS command line tool, and this is that performance subcommand that you had brushed over a little bit. And so this just lets you run some performance tests. And so that's a very easy way to quickly just pull up some readers and writers that we can start probing. So under this performance subcommand, I'm going to make use of this ping and pong. Okay. So I'll split up a ping, split up a pong. They'll communicate with each other, and then we can start poking at them.
Sounds good.
So Cyclone DDS performance ping. So now we spooled up the ping, and you see there's no data communication happening right now. So I'll open up a new tab, and then I'm going to run Cyclone DDS performance pong. And so now you see from the graph here, the data is beginning to be transmitted between the two nodes. So here's the ping, there's the pong, and their data is being, So I'm going to now follow through on what you had done before also. So we'll do the same process. So Cyclone DDS PS, we're going to list the processes here that are interacting with DDS right now. And you see here we have these two applications, DDS perf. And this is because the Cyclone DDS command line tool uses under the hood another tool that we've constructed called DDS perf to run all the performance stuff. So it's DDS perf is the application ID, and then you have those two participants, one for the ping, one for the PON. And we want to probe, let's say, into like this topic here. So again, same thing as before, Cyclone DDS LS. If I just run LS normally, it lists the information right across all of the topics, which is a little bit overwhelming.
Yeah.
So then we're going to run it, filtering on a specific topic. Oh, and I didn't copy the D. There we go. Okay. So now we have the sort of the QoS information, right, that you had seen before, but specifically for this topic that we're interested in, and you can see that the topic is interactive with these two participants. And now something interesting that you'll note, right, is you have the same sort of QoS information present, but down here for the X-type's type ID, it's set.
Yeah.
So that means we have access to type information. So let's go ahead and run that subscribe command that we couldn't run before. Right, and so here now you see these are all the messages that are going back and forth between the ping and the PON.
Yeah.
And the data here is like really simple. You have the sequence and this like key value and baggage, and they're both just default. And that's because the performance test here is just let's send messages, simple messages, as quickly as possible. Yeah. And so like if I Control C out of that, there's also the subcommand type of that allows us to inspect the actual type, like that T,
The
so the topic
type.
T, so topic T, writer T, message, so the actual T.
Yeah.
It's running type of, and now this is what the type information that DDS has described here. And so, yeah, you see it matches with the keyed sequence that's specified up there. It's a keyed sequence struct, and it has these three fields, a sequence, an unsigned long sequence, this unsigned long key value, and a sequence of octets. And that key value and sequence are both just default empty, for this one, because that's not what we're interested in with this performance test. And then the sequence number is incremented. So yeah.
Yeah, that's gonna be really nice when
when the
ROS
pull requests get
middleware
merged
layer
through,
gets
because
merged.
it'll be very fun to start prodding at just ROS.
Yeah. So now we've poked at this a little bit. Why is this useful to know?
Yeah, like why? Yeah, that makes sense. A valid question. So the point is, if you look at the architecture here, so this is similar to what we showcased before. You have your application, you have this ROS2 middle layer. That's what you're interacting with primarily in robotics applications. And underneath that, you have the DDS framework, and then the transport, and then they're communicating across the actual transport with the DDS bus, that kind of stuff.
Yeah.
Well, the point is that as you introduce these additional layers, that can introduce inefficiencies, serializing, deserializing, like overhead that in some cases might lead to latency that just means your application isn't able to function correctly. And so, for example, in the 2021 Indie Autonomous Challenge, right, and that featured three of the sister projects from the Eclipse Foundation, so Cyclone DDS, Zeno, and Isorix. Well, one of the teams had a LiDAR device that was hooked up via ROS2. And the point cloud information that they had received wasn't coming in fast enough for them to be able to compute it and then relay the actions that had to be taken by the car. And the speeds that these cars are traveling at, it's hundreds of kilometers per hour, and it's a very your latency budget there is tiny. Yeah. And so what the team did was, instead of hooking up the LiDAR device via ROS, they modified the device driver to go straight to DDS directly. And that cut the latency by 90%. And obviously with a cut like that, that's more than enough for them to be able to play around with it and get the data where it needs to get to compute it and make the car respond. As an interesting aside also, so that was in 2021, at CES this year, Polymove and the University of Alabama, they won the racing challenge that was there, and they set a new world record using both Cyclone DDS and ROS2, and they hit 290 kilometers an hour, which is incredibly fast.
So what you're saying is that we could just bypass this ROS layer here, and our data gets to the wire even faster.
Yeah, as fast as
without compromising or the compatibility or interoperability.
Yeah, 100%. Because if you remember the structure here in ROS2, it's just this thin layer on top of DDS, right? This interoperable standard. So if you just communicate via DDS and keeping the convention in mind, you're able to interface with other ROS applications, no problem.
Okay.
Yeah, so I mean, the point is that from what we've been saying so far, ROS, so Cyclone DDS, right? it's phenomenal, right? Very efficient. However, the point is it's not a panacea, right? It doesn't work necessarily in every circumstance, in every context, right? So it's important for us to consider some of the constraints of DDS.
So the first one, DDS was conceived in a time when LAN was the primary focus.
Yeah, wired networks.
Exactly, and wireless communication wasn't really available. So
certainly not widely available.
Exactly, all the focus was on that LAN, and they made it specifically with LAN in mind
originally.
Exactly,
and that isn't to say that the specification hasn't been updated, right? And people have been working on it extensively, but the point is, its initial design, some of those initial assumptions in the specification were designed with wired networks in mind.
Yeah.
And so also it's push-based only, and that just means for certain topologies it's just inappropriate to make use of, right? And for example, with the ROS abstraction for actions, right, you had 6 different topics that were being communicated against for providing feedback. Maybe it would be nicer to have a single channel there, and I guess on the ROS side that's how it's abstracted, right? But there's other some topologies that the push-based architecture is just inappropriate.
Exactly.
On top of this, there's
this is a part one.
So discovery. So that discovery process, right, where you have nodes coming in, readers and writers, and they have to discover each other.
Yes.
So they send out this communication, these handshakes saying, "Hi, I'm here. You can see me. I can see you. Let's start talking." Well, they have to do that with everyone, and at least it's not factorial, right? But there's this quadratic. It's a quadratic problem.
Yeah.
And so it's just inherent to the protocol. It's not like an implementation specific thing. It's just part of the DDS spec results in this. And so that quadratic discovery coupled with multiclass over Wi-Fi can just tank networks. And so, I mean, it's interesting, you can account for these, right, knowing this beforehand. Mm-hmm. So 2 webinars ago, as part of the same, Cyclone DDS Unleashed series, Lex had done, his topic was on scalability in DDS and how do you maybe configure things or change your architecture of your application or of your topology to deal with large-scale DDS deployments. And so there are ways you can architect your system to mitigate these issues, but we wanted to instead highlight a sister project from the Eclipse Foundation, right, Zeno.
Yeah, so Zeno, it's an extremely flexible protocol. Very small footprint, and it's pretty lightweight over the line.
Yeah.
And since it's our sister project, it integrates perfectly with Cyclone DDS.
Yeah, and there's many positive things to say about Zeno, but one of its key features is the flexibility with which you can deploy it and use it to solve
some of those shortcomings.
Yeah, but also so for example, Zeno allows for peer-to-peer communication, right? So just point-to-point or broker to routed stuff, and for the routed scenario, you're forwarding data from your peers to clients and other scenarios. So one of the real benefits of Zeno is how it's able to fit inside your topology in extremely tight spaces. And Zeno can just go there with laser precision and allow you to interact and move your data around at rest or in motion or whatever. Very, very effective. And so, here, for example, is just a sample topology, right? Mm-hmm. Where you're using Zeno and you have these DDS islands that are present here, right? So within those islands, you have, for example, the quadratic discovery happening still and other things like that. But then Zeno, it's able to, its discovery, for example, is much more laser focused, and it's able to bridge those 2 DDS networks. And you can use traffic shaping to ensure that only the stuff you care about sharing between them is shared between them. And the key thing to remember here is that Zeno hasn't been designed, has been designed specifically by us looking at the shortcomings of DDS and looking at use cases, where the situation isn't ergonomic or is much more complicated. And so Cyclone DDS and Zeno make for the perfect marriage of technologies for just getting your data where it needs to get to. And so you might want to look at some more specific topologies, right?
Yeah. Let's take, for example, a teleoperation example. So similar with the race, the autonomous, you might want to have the real car also being simulated or maybe processed or whatever on a separate network, not on site.
Yeah.
So Zeno is able to do this. They're able to bridge through the WAN
Yeah,
these
these two
networks.
local area networks. And so like the normal scenario you consider with ROS, right, is you'd have like a gazebo running as your CMU, and then on that same LAN you would have your real like robot hooked up potentially, and then you can see the robot interacting and you can teleoperate via that, you know. But in this instance, and like you had mentioned with the like the Indy autonomous challenge.
That would be.
No, that's here.
Oh, sorry.
That's here. So they, in that instance, they used the Zeno bridge to punch out from the simulation, and I think the cars are running on like a special network there. And so then you're able to punch out from the simulation that the team was using to view and interact, and then punch into the actual real network running on the car, traveling at hundreds of kilometers an hour autonomously. And so, yeah, then there's also this topology here. This is an interesting scenario. This was demoed by the Zeno team at ROSCON. So basically, like this LAN environment that we have here is the same as in like the typical ROS deployment scenario that you might have. So your simulated case there with gazebo, your real case right there, they're both just able to see each other, you know, because they're over LAN. But what they did there was they used the Zeno bridge to then connect out to the cloud. So they had Zeno running in the cloud, and then via the bridge, they were able to bridge those DDS, like the DDS communication there. And then in that cloud instance, they had like a web interface set up where they could then teleoperate their like that remote ROS instance, the robot that was present there live. And they also did some other interesting stuff there, like with the Zeno plugins, they had an MQTT plugin hooked up. So then you could use like buttons and stuff to control the robots also, like over MQTT translated into DDS land. Now, we're going to be using this also as like the base for our demo. We're not going to show it with the real robot because it's like
it's a bit tedious for
like for a webinar. In live, it's awesome, but here it's and also you know that gazebo plus robot on LAN it works. But the demo we're going to be showing is this, and we'll talk about some DDS stuff and some Zeno stuff. Yeah. So to begin with, we can showcase the To begin with, we can showcase the web UI.
Yeah. So right now we have the.
This is the teleoperation.
Teleoperation, exactly. So what you just seen in the final topology, we have the web server here being served by the Zeno router.
Yeah.
And so it's kind of listening and it's waiting for data.
Yeah,
nothing's feeding.
And you see, like, there's this LiDAR section here, and it's completely blank right now.
Exactly. So the LiDAR has nothing, it's not hearing anything, the controls don't do anything. So, but we're going to connect now to...
Yeah, so that we're going to be talking, but now we can get set up.
Yes, let's do that.
So I'm going to go ahead and run the simulation. Yeah. So I need to first source the raw stuff, right? And here now I'm going to export RMW implementation equal like RMW Cyclone DDS CPP. So this is just setting Cyclone as default ROS middleware layer for communication. Okay, so we're good to go there. And so now I'm going to go ahead and just run the TurtleBot simulation, you know, for the TurtleBot 3. It's just the default stuff from the tutorials. Okay, so this is spooling up. There's Gazebo, I'm getting started. And so here we go. And so, yeah, here you see this sort of typical scenario. Down at the bottom, we have the TurtleBot, right? And then you see with these arrows, the like LiDAR information, and then what it's able to see off of this. So now if we head back to the web UI, you'll notice here, there's still no information.
Still nothing.
Still nothing, right? The simulation is spooled up, but we want to be able to teleoperate. So let's go ahead and start that. So all I'm going to do now is I'll spool up another terminal instance, and I'm going to run Xenobridge DDS, and then pass it just a configuration file that I've preset up. Okay. And so now you see that it's it's begun bridging DDS out based on the configuration that I specified. And you see here that the LiDAR information is coming.
Yeah, we're getting the LiDAR, and we can probably then send command. Yep. So we can see it driving.
Yep. And let's see if you can get it live on my side.
Right. Yeah. And so now let's confirm. Yeah. So it looks like.
Yeah.
Yeah.
And if let me try one thing. If I try pushing forward, maybe we can just catch it fast enough if the stream's latency is. Oh, there you go.
There you go. Stream latency.
Perfect.
It's useful for something.
Yeah. Okay. Oh, I held the button.
Okay, so
perfect. Stop.
Yeah.
Okay. So like that's the basic that was easy, right? Ridiculously easy to do.
Yeah.
And so if we head back to the simulation, to the where the gazebo is running. We can go take a look at like a config file, for example, and we can also, I'll just quickly run the Cyclone DDS tooling. Same as before.
Sure.
Oh yeah, here. So you see you have exactly the same structure that we had before, right, where we have all these topics, and then you have the participants. But down here now, we have another participant in this set of topics, which is the Zeno bridge DS. So this should give you an idea of how it's working, right? Zeno is running. It ad hoc joined the local DDS communications. Based on the configuration, it then began forwarding topics from this system up to the Zeno cloud. Punched out, the Zeno cloud now received that data, and we're able to communicate immediately, quickly via the web UI. Okay, so let's go take a look at the config file.
Yeah.
All right. Here we go. Yeah, so all we did was, point at the demo, right? You saw that in the web UI also.
Yeah.
Then we specify what plugins we're interested in. So here we're interested in DDS, and you have this notion of scope in Zeno where you can say, well, when I'm forwarding, I have this scope. So you could have like here the CMU scope, but you could also imagine having like a Robot 1, Robot 2, Robot 3, whatever, other simulations.
Which we define or are listening to.
Yeah, for example.
Yeah.
And in this case, those aren't being heard,
Yeah.
And there's some other interesting things here, right? So like, for example, like traffic shaping here, right? Remember all of those actions and stuff where you have like 6 topics per single like action?
Exactly.
Well, you might not be interested in forwarding all of that. So right here, very trivially, right, we're able to specify, okay, I'm only interested in the command velocity, the ROS out, the battery state, and the scan. And that information is now being forwarded to like the Zeno equivalent topics via the bridge. Another interesting thing here is that you have like these MAC frequencies, where you can say, oh, well, how frequently should Zeno like propagate an update of that information? And this is interesting, right? Because the rate at which your robot might want that information updated doesn't necessarily match the rate at which you want your remote data for this to like the teleoperator or whatever. Like you might want the battery state to not update like immediately, like for the robot.
Maybe the robot works in real time, but you care about once a
about
second or once every minute.
Yeah, and so you can optimize and shape your traffic to make this much more efficient.
Yeah.
And then there's the like discovery traffic optimizations, right? So like with the CMU ** here, just with how this is set up, you only have one message being set for all the subs and pubs. So with Cyclone, right, different messages for topics, discovery traffic, a whole bunch of stuff, and Zeno is optimizing this so that the discovery is as efficient as it can be, basically. An interesting optional extra also is like there's this REST API that's available. We'll see if I can demo it nicely.
Yeah.
Oh, forgive this, Firefox inside a virtual machine. So if we run, let's say here, localhost port 8000, this uses this like Zeno, you publishers and subscribers, so readers, writers, that kind of stuff, right? But you also have this notion of a queryable. And so this acts as like an oracle that's able to answer for you like questions that you have of your system. So here I'm interested in everything related to like the command velocities, and here I have a payload back that gives me that information, right? And there's a whole variety of things you can be interested in. If you want to be overloaded, you can just say, give me everything. And then, you have all of the information here. I suppose that's a pretty good demo of Zeno.
Yeah, so now that you know about the technology that ZettaScale has been developing and how you can use it, we should probably take a moment to discuss why.
Yeah, very cool.
Yeah. So robots are kind of like human bodies, right?
Yep.
They're a collection of sensors, actuators, and processors.
Yep.
In a body you have, of course, the brain, but maybe also
like
a
reflex.
reflex.
Yeah, for example. That's like edge computing kind of stuff.
Exactly.
React to the data as locally as possible.
Yeah. Cyclone DDS and Zeno work in tandem as this central nervous system that connects all the sensors, actuators, processors together.
Like on top of this, it's a central nervous system, right? The data should be flowing between sensors and actuators like quickly, reliably. And the point is that we here at ZettaScale have, with Zeno, Cyclone together, have done so aiming that, making sure that like developer ergonomics isn't compromised.
Yeah.
Right? Because you saw, for example, like bridging out to that, it was like super easy. And so, then, for example.
So sensors, actuators should only be concerned with their own data that's sent and received, right?
Yeah, and your architecture should be designed in a way that facilitates that kind of stuff. And also with this sort of tandem, this combination of Cyclone and Zeno, it ensures also that there isn't like a single point of failure. Right? It makes it much easier to develop architectures that prevent those kinds of single points of failures. And like a good nervous system, when it works well here, right, you just don't notice it.
Don't notice it. Yep.
Yeah. And so like with the aims of ZettaScale being set, right, like why central nervous system ensuring your data gets there on time, reliably, right, efficiently and ergonomically, it's important for us to also talk about like the ethos.
Yeah. And since ROS is open,
yeah,
so are we.
Yeah. And that's like a dependency inversion. We believe in open source and also open governance, right? So both Cyclone DDS and Zeno are donated to the Eclipse Foundation. This like factor of being open source, it's a rewarding constraint for us, right? Mm-hmm. And it ensures like, I feel like this is the only way you can truly say you have a community, right? When everyone's able to see and interact and collaborate and
work together.
Yeah, work together. And also, the benefits of this, as you would expect, it's just open source. And
exactly. You can, if you need a bug fixed or a feature implemented that you find high priority and it's not quite,
like there might be a special case for you.
For you, yeah.
Then because the source is available, you can
fork it. You can fix it. And if you want, you can contribute back to the community, and everyone can benefit.
Or otherwise, you can open issues. You can communicate with us. We have discussions on this. Pull requests are there. So there's a lot of benefits to just being open and transparent and being dedicated to that.
Yeah.
And so like following from that, with that in mind, we wanted to take a look at some of like the testimonies from people using Cyclone DDS. And so these come from the TSC reports, and they're published with every ROS release. So this is from the Humble release in 2021, and they deal with a variety of things, but here we're looking at the RMW report, so on the ROS middleware layer. And so, for example, one of our community members was talking about how they really liked the fact that Cyclone DDS was open source like ROS, right? And that all of us were extremely accessible and responsive. And for example, if you're on our Discord and you send questions or whatever, our lead developer will probably be answering your questions also, or any of the other developers here will be responding to you very, very quickly.
Yeah, and we don't really see our community as customers, right?
For sure, because it's the community.
They're our community, yeah. But we do know that our community has customers.
Yes.
So when we hear from our community that their customers' problems can be solved as easily as just switching to, for example, Cyclone DDS, that it's incredibly good motivation for us.
Yeah, 100%. And so here it's just like, oh yeah, my customers had issues. I said, let's try out Cyclone. Oh, and all their issues just worked. Excellent.
That sounds great to us.
Yeah, it's really excellent motivation for us.
Yeah.
And also, right, like we were talking about with this efficiency, performance, and this kind of stuff. Like we're certainly very, very fast, but also the other DDS vendors aren't slouches, right? Everyone's working hard. And so when you look at the TSC reports, you find people saying, to figure out which RMW layer I want to use, I just run the matrix of all of the RMW layers. I run some tests and profile things, and we see, okay, whichever one's the fastest, that's the one we can use, like fastest and most stable and whatever. And the interesting thing that you see is you have a large proportion saying, oh, yeah, I use Cyclone also because Cyclone's the fastest. And then you have other people saying, no, I use this other DDS implementation because that implementation is the fastest. So, evidently the sort of profiling, for performance can be very difficult.
Yeah.
And so here this community member is talking about how as a result of that, they evaluate the DDS vendors not only from a technical performance standpoint, but also from a more qualitative perspective, right? And how open the developers are and how eager and responsive we are to hearing from the community and addressing feedback and engaging in discussion and this sort of stuff. And so that again is very, very heartwarming for us because that's how we want to operate.
Yeah. So these community interactions that we hear and see on these reports also help direct the development of Cyclone.
Yeah.
So what exactly does that mean for the future of Cyclone?
Yeah.
Well, in 2022, last year, ROSCON was very positive in terms of feedback.
Yeah, that was the end of last year.
That was the end of last year.
Or something.
I think in Japan.
Yeah, it was in Kyoto.
Yeah. And we've heard some great feedback, positive things, but we've also
discussions,
heard some, improvement things, feature requests, stuff like that.
Yeah.
And we heard that, as it says here, many users still switch off for us, but that's great.
Yeah, we're not the current default.
We're not the default,
but they switch off of that default to us. So it's very gratifying to hear
it's
that.
gratifying. It's a pat on the shoulder.
What's also very important is to hear that feedback
Yes.
from people so that we can make sure that we address these things and improve Cyclone even further.
Yeah.
And so, for example, there was the dynamic types API. So, we were talking about that, like, it's used for a variety of things, but the easy example we were showing you was when in the tooling that X types type information was unset and you couldn't probe it. So the fact that this was worked on right now was just as a result of direct feedback from ROSCOM. Yeah? And so the pull request for Cyclone DDS has already been merged and the RMW layer 1 is open. And so when those are merged, you'll be able to just use the tooling and dynamically reconstruct your type information. And it has a lot of other interesting use case that take it. Yeah.
More. Another thing that came up from our community was static discovery.
Yep.
So this was another feature request. It's in its conception phase.
Yep.
Basically, you will be able to define your system in a configuration.
Yeah, like declaratively, right?
Declaratively before you ever operate. And so there won't be any of this
discovery.
So you tell it where things will be and what you'll want in there.
And so then when in the discovery process, instead of saying, I'm going to look for everyone, it says, oh, I know you're there. Oh, you are there.
Yeah, exactly.
And then it's just able to immediately
And that should almost entirely remove.
Well, yeah, it'll remove the overhead for the things that are statically defined. And then I guess if there's things that are like ad hoc and coming up dynamically, there'll still be the similar discovery traffic for that. But if 90% of your system you can predefine statically because you have your fleet set up, right? Then
and if it's fully static, then perfect. And of course, this is conception phase still, so none of the things that we're saying here are like set in stone.
Set in stone.
So
but these are the things.
If you have feedback, of what you would like for it, you can always.
Yeah. So like for example, drop some questions in the chat. Right
exactly.
Now. So if you have things that you're like, oh, well, I had an idea about this, or I want to direct this further. And if you have any other questions, also you can start dropping in the chat.
Because we have big ideas, but maybe you also have big ideas.
Yeah, precisely.
So we want to make sure they align.
Yeah.
Also, kind of similar to the static discovery, that something I'm working on right now, for example, is the pluggable memory allocator. Yeah. This is work to, improve performance, because we found through some testing.
So some internal testing that like memalloc, switching to memalloc off of like the standard operating system malloc, it greatly improved
performance. Yeah. And then you can also guarantee an upper bound.
Yeah, you can start using that sort of interface, to guarantee that upper bound on resource limits. And you could then swap out for like other allocators also. A variety of things there. Oh yeah, the durability service. So this is being worked on by Lex. So that second webinar on like performance for in large DDS systems, right? And so the durability service here deals with that QoS setting I was talking about before, like durability. And durability has 3 possible values: volatile, transient local, and transient. Mm-hmm. And so in Cyclone right now, the 2 that are supported are volatile and transient local. So what that means is a volatile, easy, you don't have to synchronize any histories as late joiners join. A transient local, if the writers of some instances, some messages are still alive, then they'll propagate their written history to late joiners. But transient means that if your system tanks and comes back online, everyone has their history to start working off of. And you can immediately start reacting again to the last historical state that was present. Yeah. And so the durability service is the thing that allows you to synchronize the data in the face of like writers of that data just dying.
I can see that being very important for the robot community.
Yeah, also, yeah. Oh yeah, and it's just
a nice simple one. Packages available, Ubuntu, Conan, and
I like Nix very much. So for those hermetic builds, we'll be having Cyclone DDS in the next packages imminently. So
there's lots going on for Cyclone, obviously. But we have a sister project, Zeno. So
we've been talking about.
What does the future hold for Zeno?
Yeah. So like with the next release of Zeno, right? There's the ROS 1 bridge. So ROS 2 uses DDS as its communication stack, right? Its backbone for communication. ROS 1 used a custom like TCP/IP stack that they had built. And so with the ROS 1 bridge, you'll be able to hook up systems via Zeno, like as easily as we had just showcased with the Zeno bridge. And then you can, interoperate your ROS 1 systems with ROS 2 systems, with then other protocols, or then up into the cloud over WAN, very, very easily, super simply, with all those interesting topologies we had showcased previously. Also, in addition, there's like optimizations coming to the ROS2 bridge. So do you remember like how you had those DDS topics, and so you had actions and services, and it was like a multiplicative increase in how many topics you had, so like 6 times for a single action.
Yeah.
So you had 6 DDS topics for one ROS action. So ROS is mapping those actions to these Zeno queryable, so actions and services, so that you can like via those oracles very easily and flexibly like query information about your actions and services. So it just makes it even more ergonomic. Yeah, and then finally, this is based on the webinar that's going to be coming after us. I think this is on May the 16th, and it's a commercial offering that stems from our partnership with at ZettaScale with TT-Tech Auto, and it's focused on real-time mission critical systems. So yeah, May the 16th, our CEO Angelo Corsaro and the TT-Tech Auto CEO Salvador Rodriguez Lopez will be talking about that commercial offering for that space. So stay tuned. You can subscribe to the webinar series, right? And so then you'll be kept informed for when.
Yeah, be sure to register and attend that as well. So great. This whole webinar so far, I'm sure all of you are ready to switch.
Yeah,
to Cyclone.
immediately.
Maybe just to try it out.
Yeah.
But how do you do that? So I guess this is something important to touch on.
Yeah.
Well, luckily, it's 2 commands, basically.
Yeah.
So based on whichever version of ROS2 you're using, so whether that be humble or rolling, just in this image here, install the ROS RMW layer for Cyclone DDS, CPP, and then just export that RMW implementation variable to your environment, and that will tell ROS2 to use
that
Cyclone
as the
DDS.
backend.
Yeah.
And if you want to check it, just run the ROS2 doctor command, -- report, and then you'll be able to check, oh yeah, I'm indeed running the RMW layer that I picked.
And if you have any questions on that process, the official docs are
linked here. Yeah.
very nice too. They're very helpful. And for those of you maybe video-minded like myself, there's a YouTube video. One of the community members actually made this. He found this while doing some research. He talks about why he switched and also
and
how
you want to switch, and then
And finally,
if you want to get involved, right? You're interested. You have something you want to discuss, or you have issues, or you. So then, how do you get involved? Yeah. So for Cyclone DDS, here's our GitHub links, and for Zeno also. We have the link to the RMW layer here, also the repository, so you can look at that pull request that's currently open.
Go put some feedback on, take a look at it.
And then we have the websites if you want documentation on how Cyclone DDS works or how Zeno works. You can go to cyclonedds.io or zeno.io and just take a look at the documentation. And finally, if you want to just talk to us directly, right, and you have some questions, or you want to just talk about some interesting projects that you're constructing with Cyclone or Zeno, then here's our links to our Discord, the respective Discord channels.
Yeah, well, thank you all for your time. I'm sure there's probably a few questions. We'll be able to handle them next.
So we'll just hang here and wait while people go and ask.
Yeah, so go ahead and post those questions in the chat.